Today I'm going to talk about faster algorithms for bounded liveness in graphs and game graphs. This is joint work with Krishnendu Chatterjee, Monika Hensinger, and Saga Kahle. My name is Alexander Swozil. So, bugs are mostly nuisances, but they can also cost human lives and can be extremely expensive, as is apparent in these notorious examples like the Therac 25, a medical machine which killed people, and the Ariane 5 rocket, which crashed notoriously due to software bugs. One solution for finite state systems is to prove that the system is correct. And one way to do that is using model checking. Okay, and so what are the inputs to model checking? A system and a system specification. The system is transformed into a model. The system specification is transformed into properties. Both the model and the properties are then fed into a model checker, and the model checker outputs correct if the model suffices the properties, and that means that the system suffices the system specification, or it will output a counterexample if this is not the case. So in this case, you need to modify either the system specification or the system is incorrect. Another more ambitious approach is to, given a system specification, transform this system specification into a correct system. This is called synthesis. So what kind of models are we considering? We consider, first of all, a directed graph, which models closed systems, that is, where player one, or the system, controls all states. This has relevance in model checking, as we just discussed. Here, the vertices represent the system states, and the edges are transitions between the system states. The number of vertices is n, and the number of edges is m. Game graphs, which we usually denote with gamma, model open systems. That is where player 1 is the system and player 2 is the environment or the adversary. And this models interaction with an environment. This arises in reactive synthesis. And formally, we partition V into player 1 vertices V1 and the player 2 vertices into V2. And as you can see below, here is an example of a game graph. Okay, so system runs. So how do we model system runs? First of all, we place a token on the vertex which represents the initial state of the system. In the example, it's V1. This vertex we call start vertex. Then, if the token is on a player 1 vertex, player 1 moves the token along one of the outgoing edges. So in this case, he can only move the token to V2. And now, if the token is on a player 2 vertex, so this is for games, player 2 moves the token along one of the outgoing edges. And here he decides to move the token to V4. In this way, we create an infinite sequence of vertices, little omega, which we call play. And a common technical assumption is that every vertex has an outgoing edge. So this needs to be, this we need to assume, because otherwise we don't create an infinite sequence. But it's a common technical assumption because we mostly consider reactive systems. And the set omega contains all possible plays in gamma. And so as you can see, this play is now V1, V2, V4 because due to the facts that we just described, and also the play is in big omega. Okay, so now to the system specifications. So how do we model them? We model the properties of a system using objectives. And formally, objectives are a set of plays. And we denote them usually with phi if we do not specify them further. And it's a subset of omega, of course. So let X be a set of vertices. I will now describe some canonical objectives. So first of all, the reachability objective. So reachability of X, a play is in this objective if the play visits a vertex in X. So as you can see, now consider the example below. With the green edges, taking the play resulting from taking the green edges is V1, V2, V5, 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 and so on. And so obviously the play is in reachability of V5 because it reaches V5. Then the next objective we consider is safety of X. Here, a play needs to visit only vertices in X, okay? And so this play that we just considered in the example is not in safety of V5. Why? because it visits v1, for example. Then we consider Büchi of x. And so here the play needs to visit a vertex in x infinitely often. And here little omega is in Büchi of v5. Why? Because it visits v5 infinitely often. Then we also have Ko-Büchi of x. Here the play needs to visit only finitely many vertices which are not in x, and then it needs to stay in x. So this play is in Ko-Büchi of v5. Why? Because it only visits v1, v2 before looping in v5. And so it's in Ko-Büchi of v5. Good. So these are canonical objectives. And now here are the objectives that we considered, especially in this work. So first of all, we considered the bounded Büchi XD objectives. Those are not just arbitrary objectives, but they're stronger than Büchi of x. So here you can model now that a good event must happen every at least d steps. So from some point on, a vertex in x needs to be visited every at least d steps. So here is the formal definition, and you can assume d to be less than or equal to n, because otherwise you can just compute the Büchi condition, okay? So just for the example now, consider the play which results from taking the green edges. This is v1, v2, v5, v6, v5. And the play is in the bounded Büchi of v5-2 objective. Why? Because it visits v5 every second step. Okay, so that's pretty easy and pretty cool. And it's just stronger than Büchi. Okay, and now we also consider the bounded Ko-Büchi objective, which is weaker than Ko-Büchi. Here we need to visit not every vertex in x after some point. This is Ko-Büchi, but we need to visit at least the consecutive vertices in x infinitely often before visiting another vertex which is not in v without x again. So consider, for example, the play in this example, and then notice that the play which results in the example is not in bounded Ko-Büchi of v5 without v without v5. Now that's a different vertex set than we had in the other objective. Why? Because we visit v6, which is the only vertex qualifying as v without v5. But then we always visit v5, and in this way we never visit two consecutive vertices in the desired set. Consecutively. Okay, but consider now another example following the green edges again, and this play is not in bounded Büchi of v5-2. Why? Because we visit, for example, v3, v4 infinitely often, and then and this contradicts the requirement that we visit v5 every second step. Little omega, on the other hand, is in bounded Ko-Büchi of v without v5 2. Why? Because we visit v3, v2, and v1 and v4. So we visit v3, v4, v1, v2 consecutively, infinitely often. So we are happy. Okay, so the play is in the objective. Okay, so now what kind of algorithmic problems did we consider? What are the algorithmic questions? So for graphs, the question is, if there is a play in the objective from the given starting vertex. So if we can find such a green path from a given starting vertex for an objective. In games, now there is the environment, so we need to ask the question if player 1 can force the play in the objective despite player 2 from a given starting vertex. And now the most important question is computing the winning set. This includes all starting vertices where player 1 can force the objective phi starting from V. And of course, in this work, we considered the objectives bounded Büchi and bounded Ko-Büchi. Okay, and just as an example to clarify the notation, W1 of Büchi of V5 includes only V3, V5, because those are the only vertices which can visit V5 infinitely often. V1, V2, and V4 are not included because V2 can so player 2 can choose the red edge in each play or at each run. And so And for player 2, the winning set of Büchi of e5 are all vertices because he can always choose to take the blue edge. Okay. So now let's just summarize our contributions very quickly. So first of all, we considered the bounded Büchi objective in graphs. Here, the naive algorithm is an n-cubed algorithm, and we provide a subcubic algorithm. Okay, we improved the naive algorithm by a factor about square root n. And then in games, there is a very naive algorithm in n to the 4, and we improved this algorithm to get an n-cubed algorithm. And for bounded Ko-Büchi in graphs, we found a linear algorithm, and for games, you can use the same algorithm as in bounded Büchi. Okay, so I will explain the blue algorithm, the algorithms that I marked blue in this table. So now let's dive right into it, and I will first explain the naive algorithm for graphs. Okay, so to get this result, we need to first define a key tool which we use for solving the bounded Büchi objective. So first of all, given a graph GVE and a bounded Büchi objective XD, we construct the D plus 1 layered graph G star as follows. So for V star, we copy the Büchi vertices, which are the vertices in X, okay? I will call them Büchi vertices or vertices in X, and they're called V just to distinguish them from the other vertices. We copy them to the layered graph G star. So this is the zeroth layer into the zeroth layer, and the other vertices are duplicated D times. So V1 is put into layer 1, 2, 3, and so on up to D, and so on. Yeah. And for the edges, we just follow the original edge relationship, and edges now just always go into the next layer, except edges from the last layer, because here we just ran out of layers, so we just keep them in the div layer or layer D, or because we count from 0, it's the D plus 1 layer, but we keep it in layer D, and edges 2x, so to the Büchi vertices. Because there's only one copy, these edges always go back basically in the graph to the 0th layer. Okay, so now we are already ready to describe the naive algorithm. So first of all, we compute the SECs of the graph and then construct the layered graph that we just described for each SEC. So and now we throw away the last layer, which might also include loops. Okay, so we just throw it away. We don't care about it anymore. We remove all edges to it. We remove all edges from it. Just remove it. And now notice that any cycle that we find in this new layered graph G star visits a vertex in X every at most D steps. Okay, why is this the case? Because we follow the original edge relationship on the first hand, and those are the only edges that go back. So if we project this cycle back to the original graph, we will also visit a vertex in X every at most D steps. So that's it. We just find a cycle in the layered graph now, G star, and return all vertices, and then if we can find a cycle in this layered graph G star, we label it the whole SEC as good, because obviously the SEC can reach the cycle, and then return all vertices which can reach a good SEC. And okay, that's a very easy algorithm, very straightforward, but it's in O of n to the 3 time due to the fact that we describe this D-layered graph which has dm edges. So, and cycle detection, also the construction, takes number of edges time. Okay, that's it. So how did we improve it? Okay, so again, we compute SECs, and the input is again an SEC and the Büchi objective. And so the first thing we do is we sample square root n log n vertices into the set S, into a set S. So you can see on the right hand side, that's the SEC. We just sample square root n log n vertices into this set S. And for each vertex in S, we do incoming and outgoing breadth first search in the original graph. So this takes time, m square root n log n. This is also the running time that we are aiming for. And while doing those BFSs, we store the distance from a Büchi vertex to S and the distance from S to a Büchi vertex for all S. So sorry, for all S. Okay. Yeah. Okay, great. And then we compute the layered graph G star, but now just up to level square root n. Okay. So this is very easily doable in n square root n time. Okay. And now here is the trick. If the distance from BS, if the distance BS plus the distance from S to B prime, so we do this for all vertices in S, and then we consider all pairs of Büchi vertices, is less than or equal to D, then we can add an edge B to B prime in this layered graph now. So this is the green edge. And as you can see in the example, the distance from V8 to B1 is 1, and the distance from B1 to V8 is 8. We got this information from the BFSs. Their sum is less than or equal to 9, which is less than or equal to D, and therefore we can add the self loop. And as you can imagine, this already means that this is a good SCC. Why? Because we can just run cycle detection on this layered graph G star again, which now only has square root n layers. And this is easily doable in n squared square root n time because it's reduced. It's reduced number of layers. And the proof intuition is that and we can guarantee with high probability, because we sample log n vertices, and this just turns out to be the math, and we can guarantee with high probability that this algorithm finds every cycle. And why is this the case? Because the probability that a sampled vertex is contained in a long path between two Büchi vertices is high, okay, in a long path. And the short path we take care of with this layered graph. And so we obtain a one-bounded arrow because we might miss some large paths, obviously. But we can make this one-bounded arrow arbitrarily small by just sampling more vertices, okay? So that's the idea for this algorithm. And now let's go to games. Okay, so how do we extend this result to games? So we construct something called the layered game graph, but it's not really important. That's not really difficult. So we just, if a vertex was player 2 vertex in the original graph, it's now a player 2 vertex in the layered game graph gamma star. Okay, so we extend the partition naturally, and the rest of the graph stays the same. And we are already ready to describe the naive algorithm. So the key difficulty is that for games is that there is nothing like cycles or partitioning games into SSEs, because player 2 can mess with this cycle notion and SSE notion. So instead, we use the Ko-Büchi of X condition to force the play in the good area of the graph. And you can already imagine what the good area is. It's marked green. It's just the first D-1 layer. So after all, we want to stay in this area after some finite amount of steps in the last layer. And in this way, again, we obtain correctness, and we obtain all the vertices which visit a vertex in X infinitely every D-1 steps. Okay, so here player 1 is able to force this due to the Ko-Büchi winning set. And then you can project this back to the original graph and output the reachability to this set. And because we constructed the layered game graph, we now have n times d vertices, which is n squared, and the running time for the best algorithm for Ko-Büchi is n squared, and so we obtain a total running time of n to the 4. Okay, so how do we improve this again? So to improve this, the running time of this algorithm, we used the hierarchical game graph decomposition by Chatterjee and Hensinger in Journal ACM 2014 as a key idea. So we augmented this. So given, again, the bounded Büchi objective and gamma, we first construct the D-layered game graph, gamma star as before. And then we perform a loop over log n subgames gamma star I of gamma star. And how does this subgame gamma star I look like? it contains the same vertices, the same partition of the vertices, but now we just contain a subset of edges, okay? And this subset of edges I cannot describe in detail due to time constraints, but so EI star is a superset of EI star minus 1, so E star I minus 1 of the previous iteration. It contains at most 2 to the I and D vertices, and E star log n is equal to E star, the original edge set of the layered game graph. And yeah, caveat, E star I is selected very carefully to ensure the correctness of this procedure. And then what we can do, and this is possible in the number of edges, O of the number of edges time, is to compute the winning set of we determine if the winning set for player one of the Ko-Büchi condition of the vertices in the first d-1 layers is empty. Okay, this can be done in the number of edges. And we can compute this. And now there are three possibilities. So when it's not empty, we remove it from from gamma star. Okay, and this is a valid due to the construction of, I did not explain this in detail. We know it's correct, so we add these vertices to the set W star. So from these vertices, player one is winning. We set I to 0, so I to 1, sorry, that's a typo, and go back to step 1. Okay. So on the other hand, if it's empty, then we need to add more edges from this gamma star graph and consider the next iteration. Okay. And if it's equal to log n, we just return the set W star and terminate the algorithm. And so the running time, we can now, will now give a short intuition about why this is fast. This is due to the fact that this edge set EI star has at most O of 2 to I and D edges. And so the step 3 is in O to the 2I and D time. And also, this is another big contribution of this hierarchical game graph decomposition. We can guarantee that if W is non-empty, then the size of W is already larger than 2 to the I minus 1. Okay, so this is from Chatterjee and Hensinger 2014. And what we found out or contributed is that due to this layered game graph construction, we can add a times D to this size. Okay. And now we charge O of n to each vertex in W and to pay for the running time of step 3. Okay? And because we remove those vertices, we make a lot of progress, and this set is large. This we can prove due to the hierarchical game graph decomposition and the layered game graph. And because we can only remove ND vertices, we know that the total running time is at most n squared d time. Yeah, okay, here's a short, here's a sketch of the algorithm. And yeah, let's finish up. Future work is to implement the algorithms. And another very important open question is if we can separate Büchi and bounded Büchi. In graphs, this would mean either finding a lower bound for bounded Büchi in n to the 2.5 log n time. So either find a lower bound which says, okay, we need at least n to the 2.5 time, or finding a faster algorithm, which, yeah. And in games, we consider the same questions. And yeah. And so it's very important also to implement these algorithms because we want to find out what works in practice after all. And another important open questions would be symbolic algorithms. Okay, another reference is the reference here for the 2014 paper is here. Thank you.